When did we discuss?
Seems like you're making decisions without.
It will hurt as your business.
Well, it allows us to save on food. Even less actually, because we just add some nutrients to the recycled, nondescript, substance. We're the scam company that is obvious.
Why did we lose that?
Legitimate, excuse you.
Here we go.
How dare you? We are legitimate businessmen.
Hello.
I don't remember when Alex has a word like this.
Shut up.
All right, let me see if I can get this one working. Last week it didn't cooperate. Maybe it will today. So Lily can see people.
Darn.
Permanent office on investments. Yes, it's space pilots.
Maybe not.
And if you look at the technology, it'll say space X, but we have nothing to do with that. So don't worry about that. I don't know why my Siri is going off. I didn't even mention you. Oh no, Elon's listening. Oh no.
Hi.
I think Elon listens to lots of stuff. This does not want to go because it just keeps saying
He personally listens to
it's
all the
trying, but it's not getting anywhere. I don't know what's up with this guy anymore.
Point out.
Okay, so let me stuff back out.
So.
Just give you one pink deck after the trip. Because you got it.
40,000. How 40,000 for good?
Don't know. Oh, Drew, I think this is Drew. And
Alan dead, but I would.
Excuse you. You don't go. Yesterday.
James.
We start your training tomorrow.
Jack,
Yeah.
you were starting.
Yeah, you have about 5 hours of training, then you're going on the first.
Alex, I'm right next to you. Liam is. Don't yell at him. All right, let's see what anything
It's
else.
not really that hard, just push the button when you told me.
So everything else I
Oh,
have.
yeah, your face shrinking.
Y'all listening? Most everything else I have in here is stuff that like didn't have a name, was just laying around. So if you are missing something and you wanted it to be in your binder, come ask me and I might have it. All right, this is a fun lesson. And I'm getting up on this stuff not working here on the guy in the front. So, oh well.
It is fun.
It's actually harder to get to the sun than anywhere else.
So let's start. All right, gang, you ready? You ready? You ready? Got your brains turned on? Okay, guys. Dudes in the front. Chitty chat, 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 chat. All right. Here we go. So now we are moving on to fossils, rock records. Yay. There's some really fun stuff in this lesson. I like this one so much more than some of the ones that are just kind of more dry and about, here's what the rocks look like. This is cool because it goes kind of back towards biology, which you guys know is my wheelhouse. So we're going to talk about the geological time scale. This is a nice little spiral here, which makes it a bit easier to see considering, like I was saying, it's quite a long timeline. All right, so we have a time scale that we're going to divide Earth's history into units so we can talk about it from its origin to its present. This is just like we say we have years, months, days, hours, minutes, seconds, right? Nanoseconds if you want to be so, or milliseconds. So we have eons, eras, periods, and epochs or epochs. So here we are today. This is where we are. Do you guys remember when we did the first video, the first global warming video? Drew, what time period did the polar bears live in that we were talking about? You remember? Yeah, does anybody remember when we were talking about, did the polar bears survive such a time period? Do you remember? So it was talk about the hot mid Holocene warming period, right? So this is where we are. This is the Holocene. Like, I mean, we're in it. We're still at kind of the end of it. We hadn't even left this space of geological time when we were discussing global warming. Remember? So this is another thing I want you guys to keep in line, as keep in mind as we work towards the next set of videos. Because remember, we're gonna watch 2 more documentaries, because we watched the world is ending. No, it's not. Now we're gonna watch the answer to no, it's not. Yes, it is ending, and then the answer to no, it's not ending. No, it's not ending. Right. Those are what we're gonna watch next. So now that we're in geological time, though, I want you to really keep this in mind. Like, remember all the discussion of warming and whatever we're talking about right here. Yes.
So the documentaries are just
And here's my data, and I'm going to throw it at you. Well, here's my data, and I'm going to throw it at you.
Why your data is wrong.
And here's the same data, but I'm interpreting it to mean this, and you're interpreting it to mean that.
So you're wrong. So it's a bunch of just smart preschoolers.
Yeah, well, kind of. You know, it kind of, when they get argumentative, it kind of does seem that way sometimes. All right, so keep this in mind. We're going to look at here. So geologic time. Oh, and let me tell you this real quick. Yes, I know that last test had some weird stuff on it. I don't, like I tried to explain in the email, it's really weird if I see a change, and sometimes I don't see something until after I've uploaded it and I see it and I go back and I want to change it. If anybody's opened the test, you don't even have to have started it. If it's open, it locks me out from changing. So, yeah. And if it does that, then I can't make a change. So I ended up just deleting the confusing questions for anybody that took it after that point, because it was just, it wouldn't let me fix it. It's so annoying. And by the way, sometimes it does those spaces. Like somebody noticed the space, I think Chloe did, the space in the word than. It does that after it formats it as a test. So I have to like go back and look at them all and see if there's formatting issues. There was another one I found after Chloe pointed out hers, but it only shows me a snippet unless I click more, and that word was beyond the more, so I hadn't caught it. All right, so what are our anyway, to make the point I was trying to make before my brain goes off on another train ride somewhere else. The questions that you missed because I had to delete them might show up again, like maybe on homework. Just saying. Yes, sir. Oh, we're getting there. All right, so your your geologic time periods in order from the longest to the shortest. All righty. Who can give me our longest? All right, Yusuf, what's the longest? That's right. Okay. You got, or shortest, but I said it the other way, shortest to longest. You are right, though. Sure. I am having a day. So your shortest is your epoch. And if you look right here, this is the length of your epoch. It's just this little bit here. All right. What's the next one, Milo? Period. All right. And Liam. Era. And lastly, Piper. Eon. All right. Sometimes you'll hear people say, I haven't seen you in eons. You're like, wow, that's a lot. That's a lot of time. I also have this, this came with the fossils. It's cute, but it shows you like where you can find. So if you look up here, do you see where it says, let's see, Quaternary period? All right. And then we have it broken down into Holocene and Pleistocene, right? Well, if you look here at the Quaternary period, it's got humans here, but if you take the whole Cenozoic, everything that's blue here, that's yellow on the TV, but that's blue here, these are all the organisms that evolved during the Cenozoic, existed during the Cenozoic. And then your Mesozoic is the green, and it's green on both, right? And then your Paleozoic, this is your big burst of life, right? And it's actually kind of periwinkle here and blue here. But you can see here, like, that's a lot of organisms to pop up all at once. Some of them are fairly complex compared to others, all right? So on the geologic time scale, the smallest unit of time is called an epoch. There's no question there. So we are currently in the Holocene epoch of what period? What period are we in? Okay, Alex.
Cenozoic, Cenozoic, something like that.
Cenozoic. Do we agree? Disagree? What do you think?
Quaternary.
Quaternary?
Not part-
So
Oh,
we are in the quaternary period. Okay.
not, yeah.
So the greatest collection of fossils have been found, and paleontologists have more detailed knowledge of the events that occurred during the current time period. Oh, gee, that's a hard question. Why? Why do you suppose that is? Why do you suppose they have the most information about the current time period? Yeah.
Because that's what they've seen the most.
Yes, most recent. You're most likely to have that information.
It's also the highest up, so we don't have to dig down as far.
That too. So and once you get down deeper, you start getting, if you get deep enough, you're getting into metamorphic stuff and you lose fossils. All right, so what is an informal geologic chronological term for the proposed epoch that began when human activities had a significant global impact on the Earth's ecosystems? Do you guys know this one? All right, Yusuf, do you know it? Mid-Holocene, what do you think?
Thought it started, it was like the Holocene or something like that.
So this is in
Anthro.
Anthropocene. Okay, here you go. We're using this scene here. See it? Here it is. It's everything that's in this last little chunk of space here. We got Holocene, Pleistocene, Pliocene, Miocene. All right, what's anthro?
Human, mankind.
Yeah, human. Give me anthro in another word.
Anthropomorphic.
Drew. Anthropology, what is that? Study of people. Give me another one. Alex,
Anthropomorphic.
what's anthropomorphic?
It's when you give human character, well, it's an adjective or an
Yep,
adverb.
guys back there. Uh-huh.
Basically, when an object has had human characteristics
Mhm.
applied.
Or another organism. For example, somebody give me an anthropomorphized something. Yeah. Mickey Mouse is perfect. He is very anthropomorphized. He walks on 2 feet. He wears cute little pants, right? Okay, that's not something mice do. We have anthropomorphized him. And instead of an animal, what if it's the
Barn door.
what if it's the wardrobe in Beauty and the Beast? Or any of the characters in Beauty and the Beast, right? Yes. The pig in what? I don't, oh, Diary of a Wimpy Kid,
Yeah.
a pig. All right. All right, so
Anyways, a little short.
So we have periods and eras. So let's compare them here. So your periods are usually measured in terms of tens of millions of years to hundreds of millions of years. And they're defined by the life forms that were abundant or became extinct during the time in which specific rock deposits were deposited. So we look for specific rocks, and then we look for life forms that were abundant or became extinct, and we're covering a period of tens to hundreds of millions of years, and that's how we define a period. So it has to do with life forms, okay? Now, eras are longer spans of time, and they're measured in hundreds of millions to billions of years. And they're defined by differences in life forms found in rocks. So similar, but periods are more specific, right, than eras. Periods are shorter. Therefore, they're going to be more. Do you know what it means if I say something's more granular? Do you know what that means? What does it mean?
Like more zoomed in, more specific, more detailed.
Yes. Okay. So your periods are going to be more specific, more detailed, more granular, because they're shorter periods of time, and you're going to base it on when things become extinct versus when things were abundant. All right. So the Archean and Proterozoic are examples of eons. Okay. Yeah, that is too. Well, I could say that as well. And Phanerozoic, that's correct. All right, so here's the thing with that. Here's what you need to remember about these. All right, so you got epochs being several million years, periods being tens of millions of years. At most, they would move into the next section, which is your eras, several hundred million years, and your eons are about 1 billion years. Okay, and that's how we need to remember what we're doing, what's going on here with time chunks. So if you can keep this one will probably show up in your study guide for your next test, because it's exactly the kind of thing you need to keep in your mind when it comes to geologic time. All right, so how much is 1 billion? Does anybody know like what the national debt is right now, for example? Do you know?
About 3 trillion.
3 trillion? Anybody else want to give it a guess?
Too much.
The national debt?
Too much.
Anybody want to guess what it is?
2.5 trillion.
What do you think?
2 trillion.
2 trillion? What do you think, Parker?
Over 1.
Over 1 for daggone sure. What do you think?
2.5 trillion.
2.5 trillion. I'm gonna get the exact date, exact number for you. So what you think, Yusuf?
4.64 trillion.
What now? 4 trillion?
3.5 trillion.
So we have something called the National Debt Clock. It's a website if you ever want to go. And what it does is it ticks along and it gives you the current national debt, which is constantly growing because why? There you go. And it is currently at, let's say, US national debt, 31,539,778,200 and some odd thousand. It keeps going up. So that's kind of an incomprehensible number. I mean, really, like how much money is that? How much is a billion? How much is a trillion? Okay, this is how much is a billion, all right?
How are we supposed to pay this back?
How big is a billion?
We're not.
Good luck.
Sounds like a simple question, right? One that has a simple answer, probably. You may think you already know. But if you're human, and I assume that you are, translating this knowledge of a billion from an idea into a real world size is almost impossible. Let me show you. I need something smaller. The dime is the smallest of all the US coins, only 1.35 millimeters thick. So let's use the dime's thickness as a unit of measurement to help us understand really big numbers by taking a stack of dimes, laying it on its side, and seeing how far away the top of the stack ends up from our starting point.
Space.
I'm in Salt Lake City, Utah, at the Utah State Capitol building, and here is our starting point, 0, which puts 1 dime thickness almost right next to it. 10 dimes is still pretty close by, right about here, and 100 dimes is still within hand's reach. 1,000 dimes is right here, a little further away, but still pretty close. This too has 1,000 dimes in it, so I'm going to keep it with me as a reference as we move further away. Here's the 10,000. 100,000. Way over there, you can still see our starting point. But say goodbye, because that's the last time we'll see it on this trip. Let's take a walk.
Mm-hmm.
1 million dimes. Our starting point is 1.5 kilometers, or 0.8 miles back that way, which would put the billion dime mark. I don't even call it.
Walk.
Sort of long.
Yeah. Long way. Still driving.
$1 billion maybe.
Welcome to Iowa Western Community College.
Ah,
Plus Iowa. 1 billion dimes away from Salt Lake City. That's a distance of 1,350 kilometers or 839 miles, about that way. To put that in perspective, let's go to a map. The billion dime circle centered on Salt Lake City runs from the heart of the Midwest into the Pacific Ocean and from central Alberta, Canada to northern Mexico, covering an area of 57 million square kilometers or 2.2 million square miles. So why is it that when you look at the edge of a dime, you can easily figure out how big a stack of 10 or 100 would be, but can't immediately figure out where a stack of 1 billion of them would end? The answer is we're complicated. Our brains can't make sense of really big numbers because for hundreds of thousands of years of evolution, they haven't had to. Until the last 4,000 to 5,000 years or so, at human scale, there's never really been more than a couple of hundred of something that actually mattered. So instead, our brains have evolved to understand that beyond a certain point, it's not how many of something that matters, but that there is many of something. But as math and science have progressed, we've needed a way to describe just how big or how small a number really is, and whether it's comparable to another number. Part of the solution is to describe a number as being of a certain order of magnitude.
All right, click Lily there.
A number that is 10 times bigger or smaller than another differs by 1 order of magnitude. 100 times bigger or smaller is 2 orders, 1,000 is 3, and so on. Orders of magnitude give us a sliding scale that we can use to center our brain's natural understandings in tens and hundreds. But while convenient, this creates the problem that it's hard to bring our understanding back into the context of real scale. It's easy to assume that 1 million makes a big difference in the context of a billion or a trillion, because to our brains, they're all really big numbers and only differ by a few orders of magnitude. But in reality, a million to a billion is like 1 dime to this 1,000-dime stick, almost unnoticeable. And a million to a trillion, well, that's like this stick to the total distance back to Utah, which is to say, basically nothing. For Tech Laboratories, I'm Tech Adams, saying keep thinking, and thanks for watching.
So his point about how we can't comprehend big numbers because we haven't needed them in the past, right? So it's a valid point. Like people all the time will say, oh, there's a budget, or this guy made an extra $1 million this year, but he's a billionaire. That $1 million is like nothing. That's like you getting an extra buck of allowance or something. Like when you look at it, like within the scale. So now that we have a better idea conceptually of how big a billion, he only did a billion. He didn't do a trillion, right?
There's not enough space on Earth to do trillion without wrapping around multiple.
Yeah, correct. Yeah, there's no way he could have even done that with a dime. He would have had to find something else.
10 bill.
What's the geologic timescale? Well, the Earth is old, really old. It's so old that it's had 4.6 billion birthdays, but it doesn't like to want credit. Typical geologists have counted all the birthdays and made a big fancy chart to help remember them all. It's called the geologic timescale, and it's one of the most important things you need to know when you start to study geology.
Schedule your mammogram.
4.6
Okay.
million years is a long time. Let's say this represents 100 years, or about a human lifespan. That human lifespan is only 1 pixel if we zoom out to 100,000 years. We then need 10 of those to get to 1 million years. To get to 1 billion years, we'd have to add that up 1,000 times. That's a really long time. There are so many Earth birthdays that we have to arrange them into phases. These phases are sometimes called eons. The eons are broken up into eras, which are broken up into periods and epochs. Geologists are apparently fond of words that start with the letter E. The first eon is called the Hadean. It's about 500 million years when the Earth is just a hot ball of rock and the moon is forming. What's up, moon? Next is the Archean. Everything is chilled out a bit by now and the continents are forming. This takes a really long time, almost 1.5 billion years, and life is starting to form in the oceans. As the Archean is ending, that new life starts to fart out oxygen into the atmosphere. After that is the Proterozoic, which means early life, but it really means very small life. During the Proterozoic, we get the first complex cells and the first things that are made up of more than one cell. The Proterozoic is also very long, about 2 billion years. As the Proterozoic is ending, we get the first plants and the first animals. The final eon is called the Phanerozoic, which means visible life. It started about 500 million years ago with an explosion of new and crazy looking living things and continues to this day. It's divided into 3 eras. The first era is called the Paleozoic, which means old life. But what it really means is squiggly life or weird wormy life. It also means creepy crawly life. Mesozoic means middle life, but it really means dino life or life that goes roaring. The Mesozoic that killed almost everything out of roar. The third era, the Cenozoic, means new life.
but it really means furry life and flappy flying life. We also got pretty looking things that move. There's lots of different furry and flappy things. There's things that go glub, things that squawk, and things that go awoo. There's also new things that roar, but they're much fuzzier than the old ones. That's the geologic time scale. Some say that humans have changed the earth so much that we've entered a new period of geologic time called the Anthropocene. More on that next time. Until then, keep curious.
So that's the Anthropocene that we talked about briefly.
Why is his earth like in a form of?
I think it's a beard,
I think
because it's
a
old.
beard.
But I think you've been watching too many mafia movies. Like, what is it?
He's gonna apply.
Earth is gonna swim with the fishes. Okay. So we have ways to go about dating the rocks that we find and the fossils that we find. One way is absolute dating. What's the other way? The other big one? Jack? Well, that's part of absolute age dating. So the other one's relative, and we're gonna talk about that in a minute. So here's your absolute, and yes, we do use carbon. This is where we get some chemistry and some nuclear chemistry going on. Carbon-14 is when we use very frequently. So here's our difference. We have relative age dating, and then we're gonna have absolute age dating. Here's your relative age dating, okay? Your relative age dating places the ages of rocks and the events that form them in an order without exact dates. So this is done by comparing one event with another or event with a rock with another. So basically, if you know that there was a massive volcanic eruption that happened in this layer of rock in China, and then you see that same layer of rock in Tibet, but it's higher up or lower down or whatever, you still use that as like your marker, right? And you go, okay, this was an event. I could tell there's volcanic ash in this layer. So I know that these things came before that eruption, these things came after. And this is all relative. People will say, oh, like I've heard people say, is a certain salary a lot of money? Like, it is $100,000 a lot of money? Well, it's relative. Depends where you live, right? Yeah, I was about to say, if you live in California, it's not a whole ton of money. Yeah. Here it's decent. Yeah. If you lived in maybe let's say maybe you live in Uganda. I don't know how much it's worth there. Might be worth a lot more. How about in Venezuela?
Iran.
It'd be worth a ton of money, right? So it's all relative. And this is the same thing. That's what relative means. Not absolute, but relative. It's comparing one thing to another thing. So you're either comparing fossils, rock types, markers within rock layers, sedimentary stuff. Absolute, on the other hand, can give you the exact age when a rock or a fossil formed. They're pretty darn close. And it's called radiometric dating. So this determines the ratio of the parent to daughter material in the product. So what this means is elements within certain rocks some are more stable than others. Those that are less stable will try to get themselves to a more stable state. And it takes a period of time, and we know exactly what that period of time is. And we can use that to measure the ratio of, this is the unstable element we started with. It's now made itself stable over here. How much of this is left compared to this? You can take the ratio of one to the other and compare. So say it takes vibranium. Let's just make up an element from Black Panther. Okay, vibranium takes, so vibranium wants, let's say it wants to become, somebody give me another word, make up something, yeah.
Unobtainium.
No, that's a real one. What?
Unobtainium.
Unobtainium is perfect. Okay, so you have vibranium and unobtainium. Vibranium wants to get to unobtainium. And we know that every 500,000 years, like 0.1% of any volume of vibranium will become unobtainium. So we can look at a rock and go, it has such and such amount of vibranium, such and such amount of unobtainium, compare the two together, and you know, well, all this unobtainium was originally what? Vibranium. So now you can compare and see how old something is. And yes, carbon-14 is the one we typically use the most. So this is called a half-life, all right? So this is chemistry. Those of you who didn't do chemistry with me, that was 2 years ago. This is going to be kind of like a little explanation. For those of you who did it, you'll remember this probably. I hope you will. So your half-life is the amount of time it takes for 1/2 of the original amount of an isotope to decay. So what's an isotope? All right.
Radioactive element.
Okay, so in this case, yeah, that's what we're dealing with. So do y'all remember, some of you remember there are ions and there are isotopes, and what's the difference?
Isotopes have different number of neutrons.
Correct. Isotopes have a different number of neutrons. What do ions have?
Electron difference.
Electrons, correct. Different number of electrons, which gives them a charge, positive or negative. What is the charge of electrons? Negative, right, very good. Okay, what's the charge of a neutron? Nothing, they've got no charge. Where's most of the mass of an atom come from?
Nucleus.
In the nucleus, okay. Raise your hand next time, give us a chance. Okay, and where are the neutrons found? Piper. All right, so your neutrons are hanging out in the nucleus of your atom. And some elements tend to have isotopes, meaning they have more or less of the number of neutrons they need. And this makes them unstable because they want to get to their stable form, right? They want to get to the place where they're supposed to be. It's like either you have the roommate that helps you pay the rent and everything's happy and your roommate's with you and you're cool, or you can't wait to get rid of this guy because he's making you nuts. You just want the situation well, right? They have too many or too few neutrons. So your isotope, each of 2 or more forms of the same element, so same element that contain equal numbers of protons. What's a proton's charge? Yes, positive. Piper was going to say it. But different numbers of neutrons in their nuclei, hence differ in relative atomic mass, but not chemical properties. In particular, a radioactive form of an element. Okay, what do we mean by differ in relative atomic mass? Put up a hand if you know what that means. Relative, we just talked about what relative means. Atomic mass. Yusuf, what do you think that means? Correct. Which 2 are we comparing? The atomic mass of what? What are we comparing? Drew? Yeah. Yeah, the element to its isotopes, basically, or one isotope to another isotope. Yes, the elements to its isotope. So you have an atomic mass, all right? That's what it, quote unquote, weighs. Doesn't weigh, right? It's how much of it there is for every particular atom. And they're going to differ in atomic mass because they have more or less neutrons. Got it? But not in chemical properties. Why don't isotopes differ in chemical properties? Think about it. Think about it. What part of an atom is what causes it to react or bond with other things? Think. Who took chemistry with me? All right, James, want to guess? You didn't even take chemistry with me. What is it?
The electrons are still the same, but the
Right. And the electrons are where? With reference in a cloud outside. And that's what's interacting with other atoms, right? The electrons are doing the interacting. So the chemical properties are going to stay the same because they're not different. So then we talk about something called decay. So nuclear decay. When we say nuclear, we're talking about nuclear energy. This is what we're talking about, an atomic nucleus. That's all that you hear that word and you're like, oh, nuclear weapons, nuclear power. We're all talking about basically how many neutrons are there. Pretty much it. So nuclear decay occurs when the nucleus of an atom is unstable, right? And spontaneously emits energy in the form of radiation. The result is that the nucleus changes into the nucleus of one or more other elements. These daughter nuclei have a lower mass and are more stable. So look here. This is decay in particular, where they're showing you that over time you get less and less. And I'm going to show you another one, and it shows up here, I think, in the video, but this too. All right. Radiometric dating is used to determine the absolute age of a rock, and it's done by using the idea of a half-life. Yes.
They have like the daughter and the parent, like
Mhm.
uranium 238 compared to lead 240.
Yes. Okay, good. So here's uranium 238, which Yusuf just mentioned. Okay. Here's its daughter, lead 206. So over time, not only can it become a more stable form of itself, it can become a completely different element. It'll make its way into something different. And we talked about this in chemistry, that over time that can happen. So you see here just some examples and how long it takes and where you find these. Like you can use this carbon-14 test if you're working with organic materials, because look at this range, 100 years to 70,000 years. This is great if you want to know something that's organic. What's organic mean? What's it mean, Bailey? Derived from living matter. What's the big old element we deal with? Yeah. Yeah, carbon. All right. So these are carbon-based living things like us. All right. So organic matter, this is perfect, carbon-14. But if you're looking for igneous rocks and things, you want to be using some different isotopes because carbon's not going to help you much. So here's a great video with the giraffe. And it's Scientific American, which by the way is an excellent resource always.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
And a big old mammoth behind him. All right, so that's the idea of absolute age dating. You can use nuclear chemistry and get it down pretty close. And usually when you're going to date a fossil, we're going to use absolute age dating and relative age dating together. We're going to combine all our information so that we can get the best hypothesis for how old something is. Yes.
But after like a certain amount or certain time,
Mhm.
you can't use carbon-14.
Yes, correct, because it'll be gone. So it won't do any good. It'll be all gone anyway.
Then what would you do to find the?
So there are other ones, like we just saw on that other screen. There were a couple different isotopes that we can use for igneous rocks and things like that, that are just not carbon-14. Carbon-14 is the one that you probably need to keep in mind. Like, if it comes up ever on other tests or articles you read or news stories, it's just important to understand that it's for organic organisms and organic material only, right? But what you need to understand overall is that absolute age dating is using nuclear chemistry to nail it down. And remember, it just divides by a half, by whatever number you know. Like it takes 100 years for half of this vibranium to turn into, what was it? Unobtainium. Okay, so if half of that original amount, you have to have a vibranium, I don't know, 143. I don't know what vibranium's number is, atomic number. Atomic mass.
482.
There you go. So for relative age dating, we need an undisturbed rock sequence. Okay, so if you look at these Harry Potter books, it's a great example. The first one written was, yeah, the second one was, yeah, okay, and then, yeah, great. And they're in a stack, exactly the way they were written. Or if you read them in this order and you laid them down one after another, right? This is how you would see it. Now, you've got these layers and the oldest one is going to be at the bottom, right? And you're talking about an undisturbed sequence. Now, if you have a disturbed sequence, what would that mean? What does it mean by disturbed? What do you think, Piper?
It's like disrupted, so it's
Mhm.
not
Yeah, what are some things that could disrupt it?
Earthquakes.
Earthquakes, good. Caitlin, what were you gonna say? Something else? Earthquakes, yeah. Mudslides,
Tornadoes.
Tornadoes, how? Tell me how. Wait a minute. No, she's onto something.
Dig stuff up.
And they erode stuff. You're absolutely right. Erosion. Don't listen to your brother. You're right. Erosion can definitely disturb your layers. All right. So what's the word when we're talking about rock sequences? What's the word that means that you're placing something in stacks, just like those books were placed? And it conveys the idea of rock layers formed over time. Who knows the word? What's the word? Caitlin's looking. We're looking. Let's see. Chloe, you looking? Parker, I'm looking to see who hasn't answered anything yet. You answered something, didn't you? You're looking at me. All right, James, did you know? You're looking like you know? Guess. No? Nobody? All right, Alex.
Possibly juxtaposition, something like that.
No, you're close. So we're looking for superposition. Okay. This is another easy to break down word. What does super mean?
On top of.
Above, right? And position means, well, position. So yes,
There's superposition in the layers of the Grand Canyon.
yes, there are. That's a great example. If you go and look at that, or you know those, what's that? Antelope Canyon? Is that the one that like Windows has as one of its automatic backgrounds? It's that beautiful red sedimentary rock, and you can see all the different colors in the layers. So yeah, superposition is the idea that the oldest and the newest thing is always on the top. Superposition this word can apply to other things. It's not just rocks. You could apply this to a stack of laundry. If it was a crime scene, you could apply it to like maybe things stacked on top of a like victim. Maybe somebody covered him with a bag or something, and then tree branches, or you know what I mean? Anything could be superposition. It doesn't have to be rocks. So using sedimentary rock layers to map out Earth's geological history is called what? It originates from strata, which is a Latin word that means layers. Which one of your vocab words? Yeah. It's like an onion. It has layers. So this has strata in it. Anybody ever had a strata? It's like an Italian breakfast dessert. It's like layers of egg and like French toasty stuff sometimes, or sometimes it's more like lasagna is a type of strata. So we're looking for the word stratigraphy. Okay, break this down for me. We got roots here. What is it? Strat, we just said, word meaning layer. Drew. Stratosphere, that's a layer too. I'm looking for somebody to tell me about the rest of the word stratigraphy. Bailey? There you go. Okay, so it's written in layers, literally. Written in layers. Think about that. That's exactly how we're considering things when we look at the ground. Okay, so now we have some laws that go along with these undisturbed rock sequences. This first one here is going to say sediment layers are formed in order of formation so that the layer at the bottom is the oldest and the top layer is youngest. We just talked about it.
Superposition.
That is, yeah. Next time, put your hand up. Yep, superposition is what we're going for here. Okay, so that's what it looks like. There, 1, 2, 3, 4, going up from the bottom. All right. Now, what about sediments that are deposited horizontally? Liam. Okay. Original horizontality. That's a fun word, horizontality. So that could happen if there's like a slope, right? Or if the ground shifts a bit. Oh, but how about this one? Sediment layers deposit across a continuous area, which might later divide by faults or erosion. Anybody want to take a stab? Should be in your notes. If you haven't answered yet, you should be looking like Parker, Chloe. Anybody want to give it a shot? Piper, did you want to give it a shot? All right, close. Okay, lateral continuity. All right, what's lateral mean? Yeah, like,
It has something to do with lines.
like lines, right? Okay, correct. And then continuity means, what's the word in continuity that you recognize? There's a root. Continue. Okay, so continues in lines. So look at that. If you had a gully cut through there, like we go back and talk about, remember our erosion? You have a rill becomes a, oh, who's got it? Rill becomes Gully becomes stream, stream becomes river. Okay, so look right here. You've got a little gully started there. But if you look on both sides of it, you can see where you have lateral continuity from one to the other, just like your Grand Canyon example. Okay, how about this one? A fault or a molten rock can disperse into a layer of rocks. So in this picture, we're going to see it's the molten rock layer that's youngest. What do we call this one? Liam? Oh, that's a fun one, isn't it? We're almost there. So this is cross-cutting relationships. So there's an inclusion. An inclusion is a type of intrusion. Isn't this fun? An inclusion is an intrusion. So an inclusion is basically something that doesn't belong, that's included, all right? So cross-cutting means you've got an intrusion, an igneous intrusion that cuts through at some kind of an angle. It cross-cuts through. Did you lose your pencil or something? Oh, you got it. Okay. I thought maybe drop something behind it. All right. So you can get inclusions in stones, for example. Like one of the things they do when they check diamonds for their value is they look at them under magnification and they check for inclusions, which in diamonds are considered like a fault, for example, something that doesn't belong. A little extra mineral got here or there and it left a little spot. In this case, we're talking about, basically to me, that looks like a dike, right? And there's even a little sill right here. So this is messing up. Now, all of these are talking about what kind of rock? What kind of rock are we talking about with all these things?
Sedimentary.
Yes, sedimentary rock. And then right here, you've got some igneous popping in. And usually your igneous rock is older than your sedimentary, right? But if it cracks in and there's an intrusion like this, then it's not. It's going to be newer. So why is superposition important? Somebody tell me, give me a reason why the whole idea of the law of superposition. All right, Alex, you go.
It helps us identify how old each layer is, and then from that we could identify how old something in those rocks.
Okay, anybody else want to add to it? Why is the idea? Remember I said it doesn't have to do with rock even, it can be with anything. Why is this whole idea that the law of superposition is important? Think big picture. Like what are some other ways it could help?
It can help identify when events took place.
Yeah, when events took place, this is one of those like really obvious laws that you don't think about, but dude, it's important. Like you never think about this being a law, but if you came home from school one day and your phone was in your backpack and you dropped it on the floor, and then you went to dinner and you came back and you put your jacket on top of it, and you were like, wow, I haven't seen my phone since being here at class. All right, well, I went to dinner after. So if I take my jacket off, oh, look, there it is, right? It's like tracing your steps backwards. So it's used to determine the age of rock layers compared to other rock layers. What do we call this kind of dating? Yep, relative dating. Okay, relative, this is all relative, remember? So it's used in relative dating to determine the age of rock layers compared to other rock layers. Geologists use this law to determine the history of geological events, just like Piper said, faulting, folding, intrusive activity, past volcanic eruptions, and erosion in rock layers. And it's used in paleontology. Past volcanic eruptions, think back to our Cascade Mountain volcano eruption insurance lab, okay? It talked about how many eruptions there had been in the last like 1,000 years, 10,000 years. How did they know those numbers? Where'd they get that information from?
This.
So there's another way superposition is important. Oh, okay. So the law of original horizontality. Great word. So why is this important? This one is another really obvious thing. I mean, it's staring you in the face, obvious. Which way do things, if you drop things, yeah, what were you gonna say? Right. Do layers of rock form against the window like this? Would that happen? Like that's completely against gravity, right? That this is one of those stare you in the face, it's so obvious you never think about it type of things. So the law of original horizontality allows us to infer. What's infer? Drew?
Use prior knowledge to come up with the.
Right. You have to use your prior knowledge, right? It's not observing, you're inferring. So you're taking your observation and your prior knowledge and you're coming up with an idea. So it allows us to infer that something must happen to the rocks if they're tilted, for example. So forces such as those that result in mountain building, earthquakes, and faulting can tilt formerly horizontal rock layers. See, here are these sediments and flat layers, but if you saw them like this or like this, you know they didn't form that way, right? Have you ever seen rocks that are uplifted and they're tilted like this and the layers look like that? They didn't form that way. You know, something had to move it.
Like earthquake.
Exactly. All right, so lateral continuity. Okay, remember this is our picture of like the Grand Canyon idea. So why is this important? Yusuf has an idea. What is it, Yusuf?
Find the age of the dates of different rock. Even
That can be part of it. Yeah, Another thought?
It lets us see how things have been affected vertically as well.
Very true.
Like,
All right.
A mountain is created. A lot of the rock there is still the same age as surrounding area.
Okay,
It's just been lifted. Some of it's obviously gonna be different because of, well, some of it's gonna be igneous or metamorphic.
you're right. But you're exactly right. If you see that an area's been lifted, you can see that, you know, that layer here, like I said earlier, there's a volcanic eruption at some point. You know, this layer is everywhere, right? You can even test the rock and chemically it's the same ash, right? Well, how did it get, 30,000 feet higher over here than, or whatever, 5,000 feet higher over here than it is over here?
Well, ash was high enough, probably could have just fallen there naturally.
Could have, yeah, could have, absolutely, or could have been uplifted if you know that that area was different. Or if you know that, there was some sort of tectonic or seismic activity there. Jack, do you want to add something? You have an idea?
Kind of just what he said, like the different like rock types.
Yeah.
In the area.
Yeah. So you can use this to help identify the age of rocks and identify geological features that are related despite being separated. So separated by, like we said, a canyon or maybe a mountain range, something's different on one side than on the other. But you could have a mountain range in the middle here and then these same layers on either side of it. Okay. So your layers of sediment initially extend laterally, in all directions, and they are laterally continuous. And rocks that are otherwise similar but are now separated by a valley or other erosional feature can be assumed to be originally continuous, right? That makes sense. All right, so how about cross-cutting relationships? Why are these important? Remember, this is your igneous intrusion. Why would this be an important law to understand? This one's a little more thinky than the others. If you haven't answered yet, be thinking, like Chloe, Jack, Sky, think about why is it important to understand that this igneous intrusion is newer? All right, Bailey, what do you think? You can tell that fault area is younger, right? Because you've got this igneous intrusion. Alex?
Also, could tell, oh, there's a volcano here now, so
Mhm.
have fun with that. There's a volcano in your house now.
Drew? Wait
I'm
a minute. Hang on. Drew is answering. Say it again.
Say, just understand that kind of stuff can also help with other things too, because if you want to know, like, at one point, certain civilization existed, but you can also use.
Right.
Because
Because these are all relative, right? So you can use the law of cross-cutting relationships to infer a massive igneous rock below the surface called what? What did we say they're called? Intrusions, right? It's always younger than the rock layers around and beneath it. And that what is a break in Earth's crust is always going to be younger than the rock it cuts through. Bailey, you said it. What's younger than the rock it cuts through? You said it. Yeah. That's where you're going. So your igneous intrusions are younger and faults are younger than the rock they break through. That makes sense when you think about it, right? Like the fault is going to break existing rock, therefore it's younger than the rock it's breaking. Again, a lot of this stuff is like real obvious, but we take for granted that kind of thing. Like the law of superposition is probably the best example for a law that we probably use constantly in our lives and never even considered the fact that it's like, oh, you consider there's a law of gravity, there's a law of conservation of mass, law of conservation of matter, law of conservation of energy. And then you're like, oh yeah, there's also a law of superposition. You don't think about it ever, but you probably use it 100 times a day and don't even realize it. Look through your notebook. That's completely law of superposition, the way your notebook is organized, right? All right, so stratigraphic correlation.
That graph is a lot going on.
Woohoo! Somebody want to tell me what stratigraphic correlation is? First, we had stratigraphy, right? It means written in layers. So then what's correlate mean? What's it mean to correlate? Yusuf,
Like arrange.
arrange. Okay, Drew?
To see like there's like two things that happen at once. Like a
Okay.
correlation, like,
Okay. Mm-hmm. What do you think, Chloe? What's correlation? What's it mean to correlate? Thinking about it? How would you describe it? Yeah.
Isn't it a
Wait a minute.
sentence?
She's thinking about it.
Go together.
Okay, you're finding a commonality. Yeah. Okay, hold on. What?
Matching.
Matching kind of, yeah. So basically, yeah, you're finding a commonality between things. So stratigraphic correlation, is the matching of rock layers from one geographic area with those of another area. So if you look at this crazy graphic here, each of these is a different rock layer that is known to have been produced or whatever at a specific time period. And it's not always going to be at the same elevation because Earth's moving, right? And this is how you compare things. So then we have this uniformitarianism. Woo, fun word. Anybody want to try and explain uniformitarianism to me?
Well, first there's uniform.
Yeah, uniform means what? Drew?
To be uniform, to be the same, to be kind of.
To be the same. Yeah, that's great. If you think about people who wear uniforms, they all look the same, right? That's the idea of a uniform. And you can also use it like you could say a uniform, right? But you could also use it as an adjective. You could say, well, the size of the strawberries at this farm are pretty uniform. They're not like giant ones and little ones. Uh-huh.
Uniform and any one.
There you go. That's what I'm looking for. Uniform, one form, all the same, right? So uniformitarianism. Oh, there's a fun one. Tarianism. Anybody want to give that a shot?
Well, the uniformitarianism.
Yeah. Do you want to? What's Tarianism? Where do we get that? Do you know what it is or where it comes from, Drew?
You say Terry is kind of like,
Sounds like Terra.
Yeah,
yeah, like Sarah.
it does, but it's not in this case. What do you think?
Like terrain. Something like.
It's an ism. Okay. What's an ism?
A thing.
Believe.
Like a situation almost like there's communism. What's another ism?
Capitalism.
Capitalism. What's another one? Socialism. Everybody's going to political. Yeah.
I'm thinking.
What is it?
Satanism.
Satanism. Okay. All right. So it's like a state of being, right? So if you're talking about uniformitarianism, you're talking about the state of being in one form. That's a big one, right? Okay, so what's that mean? So what it means is states that the processes occurring today have been occurring on Earth since it formed. However, the rate, intensity, and scale with which these processes occur have changed. Okay, this is another one, take for granted, don't even think about. The fact that erosion is going on now, uniformitarianism says erosion happened 2 billion years ago too. Yeah, water hit things and they eroded, or wind blew things, but it happened before. That's the idea.
Before.
Right, that because if I drop this nickel, it will hit the floor. Because gravity exists today, that same state existed 400, million years ago. That's the idea, that you're the state of things being in one form, that the processes that Earth deals with are always going to be the same, but the intensity and the scale can occur. Now, why is this important? This is super, super important when you're talking about geology in general, trying to study our planet, really anything. What do you think?
Like the rate could move a little, the mountain gets taller.
That's
like,
true.
But why?
Yeah.
That force is still not today.
Yes, it is. But why is the idea that processes of the past are still the processes of today? Why is that important when you're trying to do science in general? Like, think about it. This is a This is more of a thinky, like you take it for granted, but it's a real deep thinker. Alex, what do you think?
A, it helps us understand more about the past.
Mm-hmm.
B, it helps us account for certain processes that have been happened in the past.
Right.
Like if we know that the continents have been drifted, that allows us to, well, take that
Mhm.
into account for, like, for instance, oh, I know, wait, if we know that both mountains have been growing and that continents have been drifting, that
Mhm.
helps us know more about what, like, Pangea would have looked
There you go.
like when South America and Africa were there.
Okay, this is a completely different one. So here's another example of how uniformitarianism can be super important in understanding things. All right, say I find a mummy and it's a grown looking mummy. It's like a my-sized mummy. I can assume it wasn't born the day before it died because processes are what they are. It was probably born as an infant and grew to an adult because that's what living things do. They mature. If you're a dentist and you look at your patient and your patient has a cavity, you don't think, well, that cavity grew yesterday, if you know it takes time for it to get there. Or if you see somebody with a tooth that's so rotten you have to pull it out, you don't go, well, that was healthy yesterday. Things happen they may happen at different rates. Like I get cavities easier than some people, just it's a different rate. My enamel dissolves faster than some people. But the process is the process. And this is for all of science. The process is the process. If it's the process today, it's the same process that was 200 million years ago. Gravity is still gravity. Light still acts like light. Heat still acts like heat. Electrons still act like electrons. I can't say yesterday electrons were positively charged because I feel like it. That's not how it goes. Yeah.
How about global warming?
See, that's part of it. You have to, for the information for that entire
Like, for example,
theory, you have to use this process.
I'm slower, but now it's at a higher rate because
Mhm.
humans.
There you go. Yeah.
Technically, you could say that electrons were positive because positive only means positive because humans say positive means positive.
True.
Positive could
Make
be
up a
negative.
word, right?
If everybody in the world just said, okay, positive, negative, non-negative, positive,
Right.
then it would.
It is whatever we just
Because-
decided it.
That, it wouldn't change, what we called it would change.
Yes, true. All right. So unconformity. If we have uniformitarianism, meaning one form, the state of being in one form, then that's uniform. Then what's unconform? Bailey. They aren't the same. Yeah, something is not the same. So here are 3 different types of unconformity. So we've got unconformity, our definition, you said not the same. When part of a rock record is destroyed, the erosional gap that forms is an unconformity. Yeah.
Disconformity.
Yes, that's a type of, yes, those are types of unconformity. So this is what we're going to go. So we have types of unconformity. So what do we call the type where you have a gap in the rock record occurring between folded or uplifted layers of rock and a sedimentary rock layer on top of them? Parker, look at your binder and see if you can find the answer for one of these because they're coming up. What do we call that? You've got a gap in the rock record between folded or uplifted rock layers and a sedimentary layer on top of them. All right, Yusuf,
Disconformity.
there we go. It's an angular unconformity. That's what we're going for. So you can see the angle there, right? There's an angle. Woohoo, here's an angle. And it does not conform with what's on top of it. This means that these layers were not laid in that direction, were they? They weren't laid down like that. They were laid down like this. They got moved. All right. What's this next one? An unconformity between parallel layers of, I'm sorry, I tapped it. Oh, I know you knew it. Of sedimentary rocks, which represents a period of erosion or non-deposition. That's disconformity. Okay. Now the last one is, I'll do Caitlin. What's the last one? There's your nonconformity. So this angular unconformity. So you got, oh, no, that should be nonconformity. I didn't change it at the top. I read it wrong. Okay, yes, your nonconformity. This is a buried erosional surface between a non-sedimentary rock and a sedimentary rock. This right here, this is like your plutons and your batholiths that get exposed like Stone Mountain. At one point, it looked like this. Right?
Now it's Mount Pimple.
Now it's, yes, and full of tourists. So a key bed. All right. What's another word for key bed? Do we know? Anybody know? Anybody know? Drew, do you know? Where'd you get those chips? Those aren't our chips. Cole, bring them home. You stole them from your grandmother. Okay, what is the key? What's the other word for key bed? No, okay, it is going to be a horizon marker. Okay, this makes sense. If you're looking at the layers of rock as a horizon, and you have a marker, that's your key bed. So it contains distinctive material that geologists can easily recognize in the rock record and use it as a time marker. So this is important, obviously, with relative dating, because you need to find some kind of a marker. Like I was talking about, that volcanic ash layer would be a marker. So what do we call this practice of using a key bed as a marker, as a horizon marker? Do you know, Yusuf?
I'm guessing key bedding.
Key bed. Okay, here's the big one.
I mean, that feels like.
We have
um,
stratigraphy, which is written in layers. We add chrono to it. And what does that mean?
Time.
Time. Okay. Time written in layers. So it tells you this time, I know what this time is written in the layers. And I can use this time to compare what's above and below it. All right. Or next to it. So relative age dating, here's going to use these one more time, run through them one more time. Make sure that you remember them. This is not just me talking.
How can geologists organize past geological events? By using relative age dating. Relative age dating allows scientists to determine the sequence of past geological events by comparing the order of rock layers. There are 5 principles of relative age dating: superposition, original horizontality, lateral continuity, inclusions, and cross-cutting relationships. Let's take a look at each principle. Imagine sediment deposits becoming thicker over time. Younger sediment layers bury older sediment layers. Over time, more and more horizontal layers form on top of each other and turn into rock. According to the principle of superposition, the rocks that were deposited first are the oldest. Notice how sediment is usually deposited in flat, level layers. This is due to the force of gravity. Over time, layers of rock may fold or tilt. Even though the rock layers are disturbed, you can still assume the layers were originally deposited horizontally. The principle of lateral continuity states that the sediments are deposited in large continuous sheets in all lateral directions. So let's say that a river carved out a canyon over time. Even though these rock layers have been eroded by the water, the order of the layers does not change. Occasionally, rock layers are intruded by magma. When this happens, bits of rock may break off and join the magma. When the magma hardens into rock, the broken pieces become part of it. These pieces, called inclusions, are older than the rock they are in. Sometimes rock formations may break or fracture. When rocks move along a fracture line, the fracture is called a fault. The principle of cross-cutting relationships states that when one geological feature cuts across another, the feature that it cuts across is older. So the fault is younger than the intrusion, which is younger than the other rock layers. Geologists use these principles of relative age dating to organize past geological events. By analyzing the positions of rock layers, they can determine the relative ages of the rocks.
So that makes sense. Like I said, all of it is the stuff you know, you just know it. You know, just never thought to think about or label it probably. So here's a great word, dendrochronology. Okay, who wants to take a stab at dendrochronology? Jack, you look like you want to try it.
Okay, I know this is a question.
Well, how about part of it? Any part of the word
Well, chronology is like,
means what?
well, time.
Like, yeah, like the study of time, sequence usually. Parker, you want to take a stab at dendo? What do you think? Pictures might help.
Oh. I wonder what you study.
Take a stab. Anything. Anything. Yeah, okay. So we're talking about tree rings, tree growth, vegetation, all right? The science of dendrochronology uses the annual growth of tree rings to date events and environmental changes. So, all right, stop waving, Alex. Geez. So you've got your first year, second year, and you can tell whether it was rainy or dry. You all good? Based on how much the tree grew that year. Now, when we did biology, we talked about how this is the xylem of the tree and you can see it and it's really neat. And if you remember, actually, we had a video on the Stradivarius violin. Do you remember that? That it sounds particularly different and it's like the highest quality violin. And it took people forever to figure out what was so special. And the wood was coming from a particular forest, particular trees that had endured the same exact environmental conditions, which caused their rings to be in a particular order, which caused the particular instruments to make the sound they make.
Is theoretically they could be replicated.
Yes, if you can find those exact trees, which would be tricky. So here's a good one, permineralization. All right, mineralization, we know what that is. So in the process of permineralization, pore spaces within an organism's shell, that's not an extra space, that's this weird font, are filled with mineral substances such as silica, and they come to replace what? What are we replacing? What gets replaced? We're replacing it with minerals, but what are we replacing, Drew? It's making a fossil. What's being replaced, Piper?
The bones, the organic.
Yeah, okay, yeah, yeah. What we're looking for is particularly is your calcium phosphate that's in those bones. Where's my, I don't know where my fossil went. Anyway, I thought it was over here. So like when you looked at the ammonite fossil, that shell and it's the calcium phosphate in the shell has been replaced with minerals. And look here, the little diagram. You have this little triceratops and it died on the shore. Oh, most organisms do not become fossils, but sometimes an organism may die by a body of water. Minerals in the water gradually replace the original bones. Soft tissues decompose, but the skeleton may become buried in the sediments. What's the, Alex, turn around. What's the, ooh, I think you know some Sky. What's the hardest material in the human body? What's last thing to decompose? Do you know? Do you remember? It's not bone, comes after bone. It's teeth, yeah. Okay, teeth are, has,
Forensics use dental records.
yes, this is why forensics use dental records, correct. All right. So over time, you get minerals replacing bone. You see the petrified wood on that table over there? That is not wood anymore. It's minerals that have replaced what used to be the tissues in the wood. So time and pressure compress the sediment into the rock, and then you get, oh, look, geological uplift, and now your rocks, you get your fossil poking out. That's kind of cool. So I like this part, and I want to roll through it though, because I'm watching our time, but there's some really fun stuff in here. So remains of organisms in the rock record. So what are the remains or evidence of once living plants or animals? We call them, Milo, we call them fossils, right? Okay. These provide clues about Earth's past environmental conditions, evolutionary changes in organisms over time, and they help correlate rock layers from one layer to another. All right, so there's some fossils. Oh, well, T-Rex and another Triceratops, and I don't know what that is, a raptor. So this is the study of past life forms, paleontology, ancient sea life, dinosaurs, prehistoric plants. I think I told you guys once we had a guest professor at Hollins for a semester who was a paleobotanist who was obsessed with a particular fern. He spent like 3 years studying this fern to write articles on it. Yeah. So fossils leave behind geological timeline of these ancient organisms on Earth. You guys good? But only are, sorry, there's something right there, but are only contained within what kind of rock? What kind of rock do you find fossils in? What kind of rock? Liam? Yes, always sedimentary rock. Why aren't you going to find him anywhere else, Liam?
Because it would be hard for it to get into the ignition.
Yeah, it would be completely destroyed in magma, and metamorphic, the process is going to destroy them, right? As the heat involved with, boom, metamorphic and igneous rock formation destroys fossil evidence. All right, now, Fossils that help scientists with relative dating to determine the age of sedimentary rock layers spread over distant areas on Earth are called what kind of fossil? Do we know what we call them? Yes.
Trace fossils.
Trace fossils? Anybody else want to give it a guess? Index fossils, that's what I'm looking for. All right, index fossils, good job. So index fossils have the following characteristics. They have to be located across many areas of Earth, so we call that widespread, easy to identify, they're not weird looking, you can spot them and know what they are, right? Present on Earth for a relatively short period of time. If they've been present on Earth for a long, long period of time, they're going to be multiple layers, it's not going to help you. And they have to be present in large numbers in that period of time. Three most common are what? What's the first one over here? Drew? What particularly? Y'all held it today in your hand. What is it? Chloe? It's an ammonite. Good. You had that one in your hand today. All right. Liam, what's this one?
Trilobite.
A trilobite. We've all seen that before, right? Okay. And what's this last one? Jack. Not coral. Piper? Milo.
No,
These
first,
are graptolites, okay?
first are still alive.
And they're kind of funky looking, but you can find these in rock layers. All right, so geologists use index fossils to correlate rock layers over large geographic areas to date a particular rock layer. This is exactly what we've been talking about with relative age dating. Of course, this makes sense. All right, whoop, didn't mean to click that one. So fossil insects can be found embedded in amber, did that today, the hardened sap of prehistoric trees. What is the fossilized species of an ancient organism? Who knows this one? Do you know it, Milo?
Does it have to be in that picture?
Well, it might be.
It-
Great, so it's a coprolite. We do have one over there on the table. This is important. What can this tell you about an organism? What they ate. Can tell you where they lived because you know that, maybe this particular tree grew here. Maybe that organism ate another organism. And you go, oh, I know what this is, right? It's like owl pellets, but preserved. Yes.
One time I saw going something that looks like a big area in which you're selling some kind of antique, like kind of rocks, these stuff.
Mhm.
And they were selling this much T-Rex poop.
Oh my gosh.
For like 1,000.
Oh, yeah.
That's a steal.
Yeah. Yeah.
How about we just?
So
Yeah.
what kind of, so this flash right back to your lab. You have these two things. Oh, look, this is what you made today. Form when original parts of an organism in sedimentary rock are weathered and eroded, leaving behind a hollowed impression. This is, Chloe. Imprint, what's the word? You're close. You're close. All right, Drew. It's a mold. Okay. And then when your minerals fill it, it's Liam. It's a cast. That's what you did today, right? This is exactly what you did today. All right, now next. These are some dudes. Let me watch how many on time. Okay, we're good. This is pretty, these are short ones.
Two sets of dinosaur fossils from the Jurassic period have been discovered in southwest China's Yunnan province. They are believed to date back more than 180 million years ago.
That is
One
cool.
set has been identified as that of a Lufungosaurus magnus by the Institute of Vertebrate Paleontology and Paleoanthropology.
Listen,
The fossil is 5.3 meters long, with multiple vertebrae and complete hind legs. The dinosaur is believed to have been 9 meters long in total.
The fossil we've retrieved is about 70% complete. It was buried in a stratum that dates back to the early Jurassic period. It is very rare to find such well-preserved dinosaur fossils from that period. Although some parts of the dinosaur are missing, the fossil we found will still aid in research concerning geography and dinosaur evolution, as well as the climate and environment at that time.
Another fossil, that of a Lufungosaurus huene, was found about 500 meters away from the site of the first discovery. The fossils were discovered in Yunnan's Lufeng County last month by road maintenance workers.
We found some
Imagine that.
fossils in our road maintenance work, which changed the course of the road to protect the site.
imagine that. Your job is to drive the bulldozer and you're like, oh man, there's a big old dinosaur right there. I mean, that is crazy. Milo?
Please all just sign a paper that makes clear stop eating a paper towel and put it on my work.
Stop being distracting, guys. Guys, serious, for real, pay attention, pay attention. So something I want you to keep in mind. So dinosaurs, as we know them, these big reptilian looking dudes, were pretty widespread, right? Most of our current continents had some type of dinosaur like this, okay? And sometimes they come popping out when layers of earth are moved or disrupted or get eroded, or in this case, have people drive over them. You know what else is pretty common in most cultures? Legends and myths involving dragons, everything from South American stuff to European stuff to Asian stuff. And a lot of people hypothesize that
Caves are common.
caves, yep. A lot of people hypothesize that the fact that we have dragon myths and legends in various cultures over the entire planet may be due to the fact that they found these things and were like, oh, what is that? And tried to imagine what it looked like if it was alive. And then you get this very similar type of organism. I'd love to know who found the unicorn. So what is rare? This is the type of fossil that is either mummified, like this guy, or found frozen in ice. Caitlin.
I was gonna
Oh,
say
sorry.
that,
Mhm.
the unicorn was probably based off of that rhino thing.
Yeah, that's been thought too. Okay, what's this one? Do we know? Yes.
Primary.
Original. Okay, original preservation. This is the rare stuff. Mummified animals. This is very often caves or ice. Now, this right here, I think, is one of the most fascinating finds ever for anthropologists, for paleontologists, primarily anthropologists. And I want you to consider some of what's being said here, not Lucy, when you're talking about when you're preparing to do your mammoth lab in a couple weeks, okay? This one's super fascinating to me.
That's the grandma.
She looks like she's just sleeping, she's gonna wake up in the next minute. And you just want to ask her a question, and is it just a feeling that she's really gonna come back and answer your question?
It's been 5 years since Cortales last saw the Doncella.
And I can see already that the Doncella has grown a little bit more saggy than she used to be. She is aging a little less gracefully than the other mummies, but it's probably because she's also an older patient. Says this
A study done on hair cuttings buried with the girl revealed that her hair was elaborately braided just before she died, perhaps as part of the sacrificial ceremony.
Let me see if there's any hair that's.
It's time to take a sample of the Doncella's 500-year-old hair.
Hey, look, this is a white hair. She had white hair. This says that's the Doncella's hair. This is very unusual for 15-year-olds to have gray or white hair. It's muy bizarre. It can be due to genetics. I mean, some young people do have white hair at a very early age, but it can also be due to stress. That would be quite interesting.
Cortales is not the only scientist who has taken the Doncella's hair. In 2003, a team of scientists from the University of Bradford in England sampled hair from all 3 children.
So here's the difficulties, try to get a hair with a follicle, that's really not easy.
It was analyzed for changes in chemical signatures of elements like carbon, nitrogen, and oxygen. A detailed timeline surfaced about what these children ate and how they lived. From her hair, the team discovered a countdown to sacrifice that began months before her death. And the first event was 1 year before the death of the maiden. A shift from a diet of vegetables and potatoes was changed to the food of the elite. Maize and animal protein. In only a moment, her life changed forever. The scientists believed that the maiden was being fortified for her destiny on top of the volcano.
So the Dunsea, if you're interested in looking at her, looking up some more about her, she's a child sacrifice, maiden sacrifice, virgin sacrifice, whatever, about 15 years old. It was the religion of the group of people that she lived in, her community at the time. And she was sacrificed at the top of a volcano. She's not the only one, but she's the best preserved one. And like they said, they can determine from her hair when her diet changed. So it wasn't like they just randomly picked her. They prepared her for at least a year for her death. Interesting. But that type of science is now used for all sorts of stuff. You can take the hair of a Jane Doe or a John Doe, and you could tell what kind of foods they ate, if they did drugs. And by the length of the hair, like somebody like me or Caitlin or Milo, somebody can tell what we did for a long time. We got a timeline that goes way back, right? But you know, somebody like Drew, they can't tell quite as long. They can also analyze tooth enamel now of Jane Does and John Does, and they can tell based on adult teeth and if they're children, primary teeth that are adult teeth that are not erupted and primary teeth that are erupted, what type of minerals they consumed at what point during their development and during the development of that enamel. And they can trace that back to different communities. They can say this Jane Doe likely lived in Florida when she was born, but moved somewhere in the Northeast. They can tell that now by analyzing stuff like that. So it's pretty fascinating. So fossils of, so we talk about adaptation of life forms. You guys know this one. The adaptation of life forms to change in the environment is known as what? Evolution, yep.
Why did I introduce you in Darwin?
Yes, would you like to meet my friend Darwin? I love my friend Darwin. So yes, you get things that change over time. This is, and you get a common ancestors. We talked, what's this thing called? Anybody remember? Remember, Piper? Nope. This diagram, this type of diagram? Oh, come on, it was only last year. Remember?
I don't remember what I did last week.
It's a cladogram. Okay, so that tells you about divergence of species from common ancestor. That you recognize this looks, this here shadow, that's what a modern horse looks like, but you know, before it looked like that, and then its ancestor looked like that, and then more like a deer, and then what the heck is that? So look at that. I like the name Hyracotherium dawn horse. Dawn makes sense as in the first, right? So at the end of the Precambrian, so here we are, we've reached the end. The end of the Precambrian is marked by the appearance of organisms with hard parts. All right, so prior to that, we just have squishy things, and then we start getting things with hard parts. Now, this lady is going to tell you about the little thingies she finds in the rocks. Or, no, it's a dude, I forget. Lady's a different one.
I went to Bradgate Park in Leicestershire to look at the Charnwood Forest fossils.
He's excited.
This is the first.
This is as
place
excited
in
as
the
British people get.
Where we found definitely earlier than Cambrian, older than Cambrian body fossils, fossils of animals, multicellular creatures. And they take various
We
forms.
talked about the graptolites.
They're these little round discs.
Similar type of
There
idea
are
here.
Things that rather look like kind of fronds of ferns, so from those things, and there are also these radiating regions of fronds. And it's thought that they were originally rather like sea pens, which were all kind of sitting up in the seafloor and radiating from these disc things, which are attachment points on the seafloor. The Cambrian fossils are all have hard shells. And the Precambrian fossils, such as these ones here, and the ones that we find in the Ediacaran Mountains in Australia, which are the same age, they're all soft. So we think that the difference between these Precambrian fossils and Cambrian fossils is the evolution of hard shells. And that might have been related to a change in sea chemistry, or it might also have been related to the evolution of teeth.
Ah,
And the hard shells was,
Morgan and Drew
a
left
result
their mark on the
of
rock as well.
Evolutionary arms race of animals not wanting to be eaten.
There you go. Evolutionary arms race of animals not wanting to be eaten.
Just smile
Sounds
at
like
the
you're trying to
end.
be
He was so very British about it. I loved that. All right, so We got a couple of these I'm gonna have you guys answer. So if you got your binders, have them open. I'll let you look those up and I'm gonna let you look these up. But oh, here we go. Let's look at our absolute age dating again. Which of these elements, we're looking at the one that says 21.3 on top. I don't know what page that is for you, but we're gonna look at this absolute age dating of rocks, 21.3. All right, so which element shown is the radioactive isotope, Bailey? Yep, all right, and which element shown is the is the stable non-radioactive element, Milo? Yep, nitrogen. All right, so that's just normal nitrogen. Okay, what is the half-life of carbon-14? All right, oh, do Caitlin?
2009. Not 900.
Okay, so the half-life is 5,730. If you look right here, so it's 0 years, 0 halves. Come back, 1 half-life, half of it's gone. It went from 100 to 50, so that's 5,730. Okay, so how many half-lives will it take for all but 25% of the original carbon-14 to decay, Liam?
2.
All righty, good. And what percentage of carbon-14 remains after 3 half-lives, Yusuf?
4.5.
All right, that's good. Now, how about N14 after 17,090 years? Jack, he's thinking,
After, wait,
15. What percentage of nitrogen 14 forms?
87.5.
87.5, yes. So that's what part formed. Oh, I think I wrote the wrong one there. That's what remains. That's what forms. Yes, 87.5. You're correct. All right. So now let's have a look at this fun one. All right. So who's got the crossword puzzle out? Number 1, smooth, rounded rocks that help dinosaurs digest and grind their food. Liam.
Gastrolith?
Gastrolith. Break that word down for me.
Oh,
Oh, no, they won't do the thing. Hold on. They're not on click. Hold on. Oh, they are. Why aren't they going anywhere? Gastrolith is right. You should all be on. Why aren't they doing? Okay, let's try again. All right. Gastrolith is correct. I'm clicking. I don't know what else you want me to do. All right. It doesn't like me right now. Hold on here. It says click. I'm clicking. What's it going to do on the click? Wipe away. Why are we being stupid? Do you think? Oh, that's fun.
not doing any of it.
No, that's fun. That's real fun. All right, so let's do it this way. You're correct. It is gastrolith. Hooray. All right, so our next one would be hardened tree sap, sometimes containing fossil insects. Caitlin. No, we're on number 5. 5 across. I think that's Amber. I think that's there. Yep, there it is, Amber. Okay. Process of filling pore spaces with mineral substances. Milo. Big one. Permineralization. Permineralization. Good. Alrighty. And a fossil impression is there. Jack. It is a cast. Oh, where are you? Go away. Oh, wait. That's here. Oh, wait. Sorry. Fossil impression filled with minerals or sediments. Yes, that you had the next one, correct. Go away. And then the impression is the mold. All right. Now, let's look down. Remains of plants or animals used to correlate rock layers over large geographic areas or to date particular rock layer. Yusuf, what you got?
Index fossils.
Index fossils. Very good. All right. How about remains or evidence of once living plants or animals? Come on, this is neat. You can do it, Scott. What do you call the remains of a once living animal? It's dead. It's a dinosaur, but now it's a girl. It's a fossil. All right. So then, all right. Okay. Remains of solid waste materials of animals. What do we call it? What do we call it? Bailey. Coprolite. This one? Oh, stop it. Coprolite. There you go. And then our last one. The adaptation of life forms to environmental changes. All right, it's true. Evolution. Very good. So listen up. listen up. So I am going to send a picture of what you're doing when with the fossil lab to make sure everybody understands it. Nobody forgets what they're doing. And so next week, be sure you bring in what you need to bring in. We'll be good to go. So y'all are awesome set. See you later. I'll get your test graded and returned soon. That is a mess right there. It's not straight. Okay, come take your money. There you go. I'll turn it. Let me turn it around. Go this way. All right, there you go. You're good. Wait, look.
My stickers coming out.
Hey, you didn't do much today, Oswald. What's the deal? Mhm. Yes, he was. There's number one. Disappears on click. Oh, I see what I did. It's easy. Easy. I had it on entrance, not exit. Oh, I had wiped the wrong way. I know this one. That should fix it.
Really hungry for Pringles.
Right? Because my kid just like shows up with Pringles and teases everyone with them.
My kid did the
Hey.
exact same thing.
That's funny. You took off, man. Nah, I will remember that. Guys, my husband is working. Thank you. Good Lord. Let's just make all the noise we can because it's so fun. Here's number 9.
I have to go early. I have to drop my grandparents out.
Ah. Okay, we'll see you later. Bye. Done. You should have none. Thank you, ma'am. All right, we're gonna go and click. Except for, there's rectangle 2. Rectangle 3. 4, 5, 6. 16 and 17 goes with 16. 18 and 19 goes with 18. Good boy, Ozzy. 20, where's 20? 20 and 21. 22. 23 and 24. Y'all watch your volume, okay? Thank you, thank you. Hey, I fixed it. Okay. Okay, can stop sharing now. It's unnecessary.